the part 3 of stepper motor. Now we will talk about tooth pole construction. The tooth construction of the stator and rotor of a stepper motor has many advantages. First is to improve the motion resolution of step angle, which now depends on the tooth pitch. Very small step angles can be achieved as a result. It enhances the concentration of the magnetic field, which generates the motor torque. It's been to improve the torque characteristic. The torque and motion characteristic become smoother or smaller ripples and less jitter as a result of the distributed tooth construction. In this figure, shown possible tooth pole construction for a stepper motor. There is H pole with 4-pass motor. Okay, there is a H pole. 1, 2, 3, 4, 5, 6, 7, 8. And they have 4 pace. And in the right picture, we see a schematic diagram for generalizing the step angle equation. Okay, this is the angle is 180 degree divided by P, and all of the angle is S divided by 2p theta r, where r is the rotor and the angle of the rotor, and then this is the rotor, and then S in here is S stator. This is the stator windings in every pole, and this is the stator pole, stator winding, and this is the stator pole. The stator teeth are equally spaced, but the pitch or the angular spacing is not identical to the pitch of the rotor teeth. In the tooth stator construction, NS in here is represent the number of teeth rather than the number of poles in stator. The number of rotor teeth has to be increased in proportion. In a full stepping or in one pace on, after P number of switching or step, where P is the number of pass, P is the amount of pace, and the adjacent rotor teeth will take the previous position of the particular rotor tooth. And it follows that the rotor rotates through theta r, or the tooth pitch of the rotor, in P step. Okay, in the step of pace. This relationship is delta theta equals to theta r divided by P. Okay, the delta theta is theta r divided by P. It still holds, but from the previous equation, we can modify to accommodate tooth poles. Tooth stator construction can provide very small step That is, maybe this small step is equals to 0.72 degree, or in commonly it can be 1.8 degree. Now we move to the next slide. We will talk about to governing the equation. The equation for the step angle given so far in that the number of stator poles is identical to the number of stator teeth. This equation have to be modified when there are multiple teeth on each stator pole. Generalization of the steep angle equation for the case of tooth pole construction can be made by referring to that figure. So the center tooth of each pole and the rotor tooth close to the stator tooth are shown. This is one of the possible geometric for a single stacked tooth construction, which is in this case the rotor tooth pitch, or the theta r, is not equal to the stator tooth pitch theta s. Another possibility for a single stack tooth construction, or which is perhaps preferable from the practical point of view, will be described later. There, if we have theta r is equal to theta s, but when all the stator teeth that are one to one of the bases are aligned with the rotor teeth, all the stator teeth would to another base will have a constraint misalignment with the rotor teeth in their immediate neighbor. Unlike that case in the construction used in the present case, theta r is not equal to theta s. Hence, only one tooth in a stator pole can be completely aligned with a rotor tooth. Okay, we consider the case of theta r is greater than theta s. So the theta r minus theta s is the offset between the rotor tooth pitch, and as there are n s per p rotor teeth in the sector made by two adjacent stator poles. And we can see that the total tooth offset of the step angle, or we call it delta theta, at the second pole is given by ns divided by mp and dot theta r minus theta s, and for the theta r greater than the theta s, whereas p is the number of bases and m is the number of stator poles per base. Now, noting that delta p equals to delta r per p is true even for the tooth construction, and by substituting to the equation before, so we can get the ns is equals to nr plus m for nr less than ns. And if we include the case that nr is greater than ns, we can get the ns equals to nr plus minus m. And a further generalization, if the theta r in here is greater than 2 theta s, or theta r is less than 2 theta s, as in the third case, by introducing an integer r, also we recall that when the stator teeth are interpreted as stator poles, we have ns is equals to mp. Then this equation can be reduced for r equals to 1. For the tooth pole construction, ns is several times the value of mp. In this case, this equation should be used in general. P can be replaced by ns per m. So the P can be replaced as ns per m. To converting an equation for a knotted pole construction for corresponding equation for the tooth pole construction. Okay, this is for the governing the equation. And in a single tooth construction that just presented, we have theta r, it's not equals to theta s. An alternative design possibility exists where the theta r is equals to theta s. But in this case, the stator poles are located around the rotor, such that when the stator teeth corresponding to one of the pieces are fully aligned with the rotor teeth, the stator teeth is in another piece will have a constant offset with the neighboring rotor teeth, thereby providing the misalignment that is needed for stepping. The torque magnitude of this construction is perhaps better of this uniform toothpaste offset per piece, but the torque ripples or jitter would also be stronger as a disadvantage because a sudden and more prominent change in magnetic reluctance from pole to the pole. And then this offset, in fact, the angle, the step angle in full stepping. And then when the stator teeth in pole 1 are perfectly aligned with the rotor teeth, the stator teeth in pole 2 will have an offset of delta theta with the neighboring motor teeth. This offset can be either in the counterclockwise direction or in the clockwise direction. As the pole pitch is 360 degree per pm, so we have an 1 per theta r dot or the multiplied by 360 degree per pm plus minus delta theta, it's equals to r, where The R is integer number of rotor teeth contained with the angular sector 360 degree per pm plus minus delta theta. And delta theta is the step angle for full stepping, and theta r is the rotor tooth pitch, and p is the number of pace, and m is the number of stator poles per pace. So we can get an r plus minus m equals to PMR, whereas the NR is the number of rotor teeth. It should be clear that within two consecutive poles would choose the same pace. These are the NR per M rotor teeth. As the P switching, this is the P is the switching of the magnitude of delta theta, it will result in a total rotation of theta r. Okay, this is the resume for the step modes. There is a full step, half step, and microstepping. Okay, for the full step, for example, we have 200 teeth. We will divide by 360 degree, so it would be 1.8 degree per step. And for the half step, one winding energized, other to alternate. Half of the distance per step is 0.9 degree, and the smoother operation, but 30% less torque. And this is the illustration of full step. This is one pace on for the full step. This is the first step, first pace, and this is the second pace, and the first pace again, and the second pace. And if we have to pace on, so for step A, for pace A and B, we can get in here the movement, and for B and A for B, and P and A. And this is the illustration of the half step. 1 2 peso on a half step. Okay, this is the first phase and the half step, and then go to the pace 2 and go to the half of A and B, and then go to the A, go to the between A and B, and go to the P, and go to the angle of between B and A. And for the microstepping, this is the new technology that divided each step up to the 256 microsteps, for the resulting in a step angle of 0.007 degree. So for the microstepping, there is a very little step on pace, with maximum power in pace A and pace B is at 0. The rotor will line up with the pace A as current to pace A decreases. It increases to pace B. The rotor will take small steps towards pace B until pace B is at its maximum and pace A is at 0. Then the process continue around other paces. Okay, this is the phase A current, and this is the phase B current, and this is the phase A current, and this is the phase B current. So for the phase A current, we can get the sinusoidal sinusoidal form, and this is for the phase B current, and this is the 90-degree phase for the shift. And these two chain coils are energized in varying proportion. Very small step commands for the standstill to not overcome internal friction. Microstep the size may not be linear during the full step, but the motor turns smoother to reduce a noise. So for microstepping, there's 2 steps for a full step. Over 10,000 steps per revolution can be achieved. This is in here, the resolution is not equal to the accuracy. Smaller micro steps worth relative repeatability. And the torch between 2 microsteps is small. Reduce the torch compared to the full step dual phase control. And in here, microstepping serves two purposes. First, it allows a stepping motor to stop and hold a position between the full or half step position. And the second purpose is it largely eliminates the jerk character of low speed stepping motor operation and the noise at intermediate speeds. And third, it reduces problem with the resonance. Okay, although some microstepping controller over 100 of intermediate position between step, it is worth noting that microstepping does not generally over great precision, both because of the linearity problems and because of the effect of static friction. We have seen how full stepping and half stepping can be achieved simply by using an appropriate switching scheme. And for the half stepping occurs when pass switching alternate between one passer and two passer on a state. Full stepping occurs when either one pass on switching or two pass on switching is used exclusively for every step. In both cases, the current level or state of a pace is either 0 or 1, rather than using just two current levels, which is the binary case. It is possible to use several levels of pace current between these two extremes, thereby achieving much smaller step angles. This is the principle behind microstepping. The microstepping is achieved by properly changing the path current in a small step. Instead of switching them and on the on position and off position, as the case of full stepping and half stepping, the principle behind this can be understood by considering two identical stator poles. with identical windings. So in this figure, we see when the current through the winding are identical in magnitude and direction. And we get this is the equilibrium, the 10th position for the microstep. And this is the and in the bottom we see the equilibrium position after microstepping. And this is the delta theta, and this is for the coil's current flow. This is for the E plus delta E. And therefore, an ideal two-winding variable reluctance or permanent magnet motor of the torch versus shaft angle curve, we can get the formula as H is equals to A square plus B square, and this the what in bahasa is akar dari A square plus B square, and X is equals to S divided by P divided by 2 arc tangen B per A, whereas A B per A. Okay, whereas A is torque applied by winding with the equilibrium at angle 0, and the B is torque applied by winding with the equilibrium at angle S, and H in here is holding torque of the composite, and X in here is equilibrium position, and S in here is a step angle. So the resultant magnetic field will lie symmetrically between two poles. If the current in one pole is decreased while the other current is kept unchanged, the resultant magnetic field will move closer to the pole with the large current. As the dead-end position of the equilibrium position depends on the position of the resultant magnetic field, it follows that a very small step angle can be achieved simply by controlling the relative magnitudes and the direction of the phase currents. A step angle, if we have 1 per 125 of the full step or smaller, may be obtained through microstepping. For example, we have 100 step revolution, 10,000 step per revolution may be achieved. The step size in a sequence of microstep is not identical. This is because stepping is done through microstep of the phase current, which the magnetic field generated by it. It has a nonlinear relation with the physical step angle. And still in microstepping, this formula is quite general, but it offers a little in the way of guidance for how to select appropriate value of the current through the two winding of the motor. A common solution is to arrange the torque applied by the two windings so that where some H has a constant magnitude equals to the single winding hole torch. This is refer to a sin cosine microstepping. We can get A equals to H1 sin P per 2 per S theta, and B as H1 cos P per theta, and per S dot the theta, whereas the H1 is the single winding holding torch, and then the P per 2 per S theta is the electrical shaft angle, and then give that none of the magnetic circuits are saturated, the torch and the current are linearly related. As a result, to hold the motor rotor to angle theta, we set the current through the two windings as A EA is equals to E maximum sin P per 2 per S theta, and it's same with the EB is equals to E max, but we use the cos of P per 2 per S theta, whereas the A is the current through winding with the equilibrium at the angle 0, and EB is the current through winding with the equilibrium at the angle S. And then E max is the maximum allowed current through any motor windings. So this is the explanation about the microstepping. We will move to the hybrid stepper motor. And for the hybrid stepper motor, we know from the previous slide or the previous video, we get the feature for both variable reluctance, and the PM stepper is more complex structure and thus make it more expensive. For the small step size, like the VR stepper, more torch with less power, like the permanent magnet stepper. So now we have a hybrid motor that show some resistance when the rotated without power, therefore holds the position also without power. This permanent magnet inside is laminated rotor. It have good torch and resolution, and then more expensive of course. And this is the rotor structure of the hybrid motor. We have the laminated steel, and this is for the permanent magnet. And this is the construction of the hybrid motor. We have the rotor in here, and this is the coils, and this is the magnet. Okay. And then this is the holding torch. When we achieve the position, it's not perfectly precise, but the motor can be displaced with a small torch. When a step is taken, the torch is reducing towards to the desired position. The axle moves towards the equilibrium state. Steps are lost when external torque exceeds the holding torque. Then also the calculate position of is lost. This is the position of the holding torque, and this is for the one step angle, and this is the displacement theta from an equilibrium position. The operating of the slightly sagging the magnetic field acts as a spring, audible noise due to the stepping. So if the vibration of low speeds is an issue, consider the gear types. Not only does changing the gears increase torque, but also this model improve starting and stopping responsiveness. Now, this is the graph of rotor position versus stepping force, and this is the step angle. This 2% settling time, and this is 5% settling time for the rotor position. And this is the stepping rate. Start and stop slower than a pull-in rate, and stay below slow rate in a constant operation. Okay, this is in the hybrid stepper motor. The most variety of stepping motor in engineering application. The hybrid stepper motor has two stacks of rotor teeth on its shaft. So two rotor stacks are magnetized to have opposite polarities. Okay, this is the opposite polarities for the rotor stack 1 and magnetized by north, and rotor stack 2 is magnetized S in the stator. And then there are two stator segments surrounding the two rotor stack. Both rotor and stator have teeth, and their pitch angle are equal. Its stator segment is wound to a single pace, and accordingly the number of pace is 2. It follows that the hybrid stepper is similar in mechanical design and stator winding to a two-stack equal pitch VR stepper. There are some dissimilarities, however. The stator stack are magnetized, and the interstack misalignment is 1/4 of the two-pitch rotor stack misalignment, or the 1/4 pitch. In a hybrid stepper motor, pulsar 1 is off and pulsar 2 is on with an polarity. And then for the opposite direction, the sequence is simply reversed. So we can get 0, 1, 1, 0, 0, minus 1, minus 1, 0, or 0, 1. And the step angle is given by delta theta is equals to theta per 4, whereas the theta is equals to theta r equals to theta s and equals to the tooth pitch angle. This is for the rotor teeth. We have 1/4 pitch, and this is the stator segment 1 in pulsar 1 surrounding to the stack 1. We have the stator teeth in here. For the north poles, and for the south poles we have rotor stack 2 and stator passer 2 in here.